Swayam Prabha. Digital India. Educated India.
Good morning to all of you. Welcome to this course on advanced structural analysis. This is a course that we are offering on video through the auspices of NPTEL. We are starting with the first module where we will be reviewing basic structural analysis. This is the first lecture in this entire series of about 45 lectures. Welcome once again to advanced structural analysis. So these are the modules that we will cover in this course. There are 7 modules. The first is review of basic structural analysis 1, which is what we will start with today. We will go fast over it because you have already studied that. Review of basic structural analysis 2, part of it you have studied. We will be looking at indeterminate structures. So you have learned force methods, but you have not learned displacement methods. So we will study displacement methods in some more detail. And then we have basic matrix concepts. This course is essentially a course which is matrix analysis of structural analysis. And then we will do axial elements first. They are truss elements, both plane trusses and space trusses. Then we look at beams, we look at grids, we look at plane and space frames, and we will also look at second order effects and elastic instability. So these are little advanced topics and I hope you will find it interesting. You are free to ask questions at any point. To start with, please note that the primary reference for this course will be the 2 books which I have authored. Structural analysis you have already been exposed to, except for some chapters at the end which we will cover now, and the main text is advanced structural analysis. Both are published by Narosa in India, they are paperback, and abroad it is hardbound, published by Alpha Science. So in the first module we will basically cover introduction to structural analysis, then statically determinate structures, work and energy methods. And in the next module, or in this module itself, will be these are the topics, but the last 2, force methods and displacement methods, we will cover in module 2. So if you recall, in the book on structural analysis we have 5 parts, and today we will quickly cover parts 1 and 2. To begin with, let us refresh our understanding of what structural analysis is all about. Structural analysis is the analysis of a given structure subject to some given loads, and the idea is to predict the response of the structure. As you may know that this is exactly what is expected of all sciences. You can view it as a system. There is some input to the system which we call a stimulus, and there is an output from the system which we call a response, and structural analysis is the application of solid mechanics to predict the response in terms of forces and displacements of a given structure. It could be an existing structure or a new structure subject to specified loads. And along with structural analysis we have structural design. Your real objective is to do structural design, but in order to do design you need to do analysis. In design we proportion the structures, we identify the materials, and you need to have some initial proportions to do analysis in the first place. So it is an interactive process, and there are some requirements of any structure. Can you name some? The main requirements of any structure? Strength, yes. Stability, which should come first? Stability should come first. Structure should first be stable. Strength and
durability.
Durability will come as part of serviceability. Okay. So basically there are safety related issues, and stability, strength and stiffness generally cover the safety related issues. Strength and stiffness we have covered, stability you all know what it means, and then it is not just enough to make a structure strong, stiff and stable, it must be also economical and it must look good, it must be aesthetic. So you will find that economy is, there is a trade off between economy and safety, because you need to invest more to make a structure more safe, but then someone has to pay for it. So the real challenge for a structural engineer is to just about give the right proportions so that you do not spend too much money on the structure. So we have discussed this, a structure is really a system, and we actually deal with a mathematical model of the structure. So we reduce the complex 3-dimensional structure to something that we can handle. So we need to do structural idealization, we have to reduce the structure to elements, and the elements are interconnected with joints, and there is something called internal stability of the structure. The structure must also be externally stable, especially terrestrial structures on the ground, they should not fly off, move away, and so we have to have adequate supports, and that raises the issue of indeterminacy. We will look into that, static and kinematic indeterminacy. So all this put together covers the structure, and then loads that act on the structure are of two kinds, we will come to that later. So let us look at the structure properly. So I have shown here the picture of a building, it's pretty complicated. You have slabs, you have columns, you have beams, you have foundations. So for our convenience we try to separate out the slabs which we deal with independently and separately, and we transfer the loads of that slab to the frame. So you end up dealing with the analysis of a space frame, but and that space frame is made up of elements which are, or the structure as a whole is made up of elements which are skeletal and which have also spatial elements. So spatial elements are those elements whose plan dimensions are large but the thickness is small. So for example a slab or a plate or a shell, they constitute spatial elements, whereas the skeletal element like the human skeleton is made up of line elements whose length dimension is very large in comparison with the cross sectional dimensions. And we all know that the first course in structural analysis we deal with the skeletal elements, the spatial elements is a little advanced to be taken up later. So the most general skeletal structure is a 3-dimensional space frame. I showed you a picture in the earlier slide, and a special case of that structure is a planar structure. How is a planar structure defined?
All the elements and nodes are in the same.
All the elements that make up the structure must lie in one plane, and the loads that act on the structure must also lie on that same plane. So that's how you get a planar structure, and a special case of the planar structure is a linear structure. For example a chain, where all the elements are connected in one line. So the space structure is typically made up of space frame elements. You can see a typical space frame element there. It's got 6 degrees of freedom at each of the two ends. You can describe the degrees of freedom in terms of movements, translations, 3 translations and 3 rotations in Cartesian coordinates. Also you can think of forces. So for example you have an axial force, a twisting moment, you see the double arrow along the longitudinal axis, you have shear forces in 2 planes and bending moments in 2 planes. So that's pretty complicated. So to simplify, we often reduce the complexity and go to a planar structure which is made up of plane frame elements. So in the plane frame element you just have an axial force, a shear force and a bending moment at any section, and you can see that the planar structure is made up of plane frame elements, and the grid is a special case of the space frame. In the grid you may have seen networks of beams that especially forming a horizontal planar structure, but the loads are acting out of plane, so it does not qualify to be a planar structure, it becomes a space structure. They are a little complicated, we will study how to analyze those structures. So in a grid structure you have twisting moments coming into play, and that is what makes it different from a beam, because in a beam you have just a shear force and a bending moment, but in a plane frame element you have a shear force, bending moment and an axial force. In a grid element you have shear force, bending moment and a twisting moment, but no axial force. And then you have a special case of the space frame called a space truss, and you know that a truss member is one in which you have only an axial force, the shear forces and bending moments are supposed to be negligible, and if all the elements in that truss lie in one plane it is called a plane truss. So a plane truss is also a special case of a plane frame, and if you have a chain then you have an axial system. Is this clear? So this is what we are going to deal with in structural analysis, and all these elements are connected with joints, and what is the function of a joint?
Transfer of loads and moments.
Transferring forces is the static function, but a more important function is
Constrains the displacement.
Let's take this structure. This is an elbow joint, this is a forearm, and this part of the arm are connected with this joint. This joint really holds the elements together, so that if you pull my hand it does not come off, it's connected to the rest of my body. So one of the main functions of a joint is to ensure that the elements stay together, move together, and you will allow only those movements that you would like to allow. So if you have a rigid connection you would not allow any relative movement. So in summary you have a kinematic function. The purpose is to control relative displacements. The displacements could be either translations or could be rotations. For example, the joint here at the shoulder, you have a ball and socket joint which can allow movements in all directions, and it is precisely because you allow those movements that you prevent transmission of those forces corresponding to those movements. So no bending moment is transmitted across a hinge joint, but an axial force is transmitted because you do not allow relative axial displacement. So you have two functions, kinematic function and a static function, and ideally these are idealized as either pinned joints or rigid joints. In a pinned joint you do not allow any relative translation, but you allow a relative rotation, and it could be in one plane or multiple planes. But if you have a rigid connection then it is like you have one member, one piece, there is no joint. In fact, when your bone fractures and it heals again, the two elements unite in such a manner you get a rigid connection. A fully welded connection, for example, is a rigid connection. Okay, so there is something called a semi-rigid connection, where you have some partial movement. We will not look at that in this course. And then the supports are joints at the boundaries of the structure. Here again you can arrest or allow translation or a rotation, and you get reactions when you arrest movements. Okay, so if you arrest a translation in a particular direction, you provide for a reaction. It could be vertical or horizontal or inclined, or you could get a bending moment, for example at the fixed support. Now this is a topic which I think many students really have not understood well. What is an internal hinge and how does it work? So you have here a propped cantilever AC, which would be statically indeterminate, but the provision of an internal hinge in the middle at B makes it just rigid and statically determinate. How does this behave? Well, take a look at the deflected shape, and this is something I have always emphasized. A good structural engineer is one who tries to make use of both hemispheres of the brain, the logical analytical left brain, which does all the calculations of bending moment, shear forces and all that based on equations, and the intuitive right side of the brain, which can see directly without doing any calculations, and it is necessary to correlate these two, and that is why structural analysis is a beautiful subject to develop oneself. You develop analytical skills and you also develop intuitive skills. So it is a good practice wherever possible to draw deflected shapes, and for example the curved shape of the deflected diagram must match with the bending moment diagram. So here you see that at the joint B there is a relative change in angle, there is no need to satisfy rotational compatibility, and you will find that of the two elements AB and BC, one is dependent on the other. Which is dependent on which? BC is dependent on AB. AB can stand alone on its own, it is a cantilever, but BC is not. BC will fall down because there is no support given at B. So if you had to separate out these two elements, what kind of support would you provide at B? You will provide a spring support because you can get a vertical force transfer at B, but B can move. So you should ideally model the correct element, and here a spring element is appropriate, and you can see that the load P2 will be shared, if it is right in the middle, equally by the forces at B and C, and the shear force developed at B gets transmitted to the cantilever AB, and that is how it operates, and this, so now it has become statically determinate. So it is very easy to do that. You basically invoked an equation that the bending moment at B is 0, no bending moment can be transmitted from one to the other, but even more important, you can really appreciate how this works. BC is dependent on AB. For example, the load P1 acting on that structure will go entirely to AB because AB can stand on its own, nothing gets transmitted to the support at C, but the load P2 needs the help of AB, so part of it reaches AB. And if you look at the practical construction, these are often used in bridges, you will find that it is an articulation like this, and there is a bearing provided, and clearly you can see from that detail at B that BC is sitting on AB at B and not vice versa. So another way to look at it is in this manner. Here it is very clear which is the child and which is the parent. Now I showed this picture earlier of a space frame. A space frame is also very difficult to compute, to analyze. Why is it difficult to analyze?
60 degrees.
Sorry?
Because it has 60 degrees of
Because it has
60 degrees of
not, that is not the right answer.
Statically
It is highly indeterminate. Okay, it is highly indeterminate. You need to solve many simultaneous equations to crack the problem. So traditionally you try to simplify it. So what you do is you break it up into plane frames and you make some assumptions. The assumption you make is that the frames in the transverse direction and the frames in the longitudinal direction really do not interact. They will interact, for example, if the building twists, but if it does not, if it is a kind of a regular symmetric structure, we can make this idealization. So and if it is a long building, all the plane frames are identical, so you need to analyze only one of them or maybe two of them, an intermediate frame and end frame. So it becomes much simpler. This is how it is handled, and that is a plane frame element. So under gravity loads, for example, a plane frame will look like this, and even this is a little difficult to do, and traditionally the concept of substitute frames have been used to simplify the analysis. The argument is the bending moment in any beam will really not be affected by what is happening far away from that end, and we can prove this through a principle called Mueller-Brislow's principle. So you could assume, you could take out one floor separately and assume the columns to be fixed at top and bottom. So you are actually separating out that frame, you are substituting the small frame for the big frame. There will be errors, but the order of those errors will be not significant. You have to be careful when you do this idealization. You cannot do it when the frame is unsymmetric, when the frame is subjected to sway, but otherwise you could do this. And if you want to take some more shortcuts, you could actually take out one beam, you could reduce this to a continuous beam and say that not much moments get transmitted to the columns, which is true for interior beams because the moment on the left side is more or less equal to the moment on the right side. You could reduce this to a continuous beam, and even further you could take out just one beam. But when you take out one beam from that whole big structure, you must recognize that it is not really a simply supported beam, because you get some partial fixity at the two ends, and so it is appropriate to put a rotational spring at the two ends and design for some moment. So this, we know that the bending moment diagram will look like that and the shear force diagram will look like this. The exact numbers are something that you need to find out, but a good guess is good to start off when you do modeling of the beam. For example, if the total load is W and the span is L, it is a general rule of thumb that the bending moments due to gravity load will be in the order of plus or minus WL by 10, and if you design for it, it is good enough, but of course it is not exactly so, and you can do it more accurately. The grillage looks like this, it is all in one floor, and as I mentioned earlier, the additional internal force you get is a twisting moment, which is what makes it different from a normal beam. So a grid element is a beam which also has torsion, and if the torsional stiffness is negligible, for example if you are dealing with reinforced concrete, and this kind of torsion is called secondary torsion or compatibility torsion, a concrete to concrete connection for torsion is not very strong. When this beam bends, it is going to have a flexural rotation at this end, and because it is integrally connected to this beam, that beam is also going to rotate, but what is a flexural rotation for one beam is a angle of twist for the other beam, and how much moment is transmitted at that junction depends on the torsional stiffness of this connecting beam in addition to the flexural stiffness of this beam. Now concrete cracks rather easily under torsion, and the twisting moment is nothing but the torsional stiffness multiplied by the angle of twist, not the twisting moment, the torque transmitted at that joint. And so you could have a large angle of twist, but you have a low torsional stiffness, and the torsional stiffness can degrade up to 15% in normal buildings, especially under high loads. Then you practically get no twisting moment. So often you can assume that there is no moment transfer, and this is allowed by many codes. You can treat the beam as being simply supported. So if you make that assumption, the grid element reduces to a beam element. Now we come to the topic of static indeterminacy, and it is important to realize that although we use words like statically indeterminate structures, as far as the structure is concerned, it is more appropriate to talk in terms of kinematics rather than statics. The indeterminacy is a problem that the analyst faces, it is no problem for the structure. The analyst finds it difficult to analyze a structure using simple equations of static equilibrium. So the statics is indeterminate. Statics refers to the force field. Why does it happen? It happens so because you provided more constraints than the absolute minimum required to keep the structure stable. So we use a word called over rigid or over constrained to describe a structure which is excessively constrained, and to the extent to which it is constrained excessively, you have an order of a degree of static indeterminacy. So for example, you are familiar with this is a simple truss, you know it can be proved that m plus r, if it is equal to 2j, m is the number of bars also signifying the number of unknown internal forces, r is the number of reaction components, and j is the number of joints, and at every joint in a plane truss you can have two forces that can act. You have two equations of equilibrium if you use the method of joints. That is how this equation holds good. Now here you still satisfy m plus r equal to 2j, but the structure is unstable because you have not located the members properly, you do not have triangulation here, and that segment on the right can deform, and it is important to know how it will move. It is unstable, those elements cannot take any shear. But if you provide an extra diagonal element, then you have a degree of static indeterminacy equal to 2. We have studied all this, it is just a simple introduction. So here you have an example of an unstable structure in the middle, a just rigid structure whose degree of static indeterminacy is 0, and on the right you have an over rigid structure whose degree of static indeterminacy is 2. Now here is something that we will really need to understand. It gives us a framework to do matrix analysis of structures. So take a look at this simple plane truss which satisfies m plus r equal to 2j. You have 11 members and you have 7 joints. Each joint has 2 degrees of freedom, so you have 14 degrees of freedom. Let us first see in what all ways we can apply forces. So you can apply F1 and F2 orthogonally. For convenience we choose x and y directions, and we can keep numbering them F1, F2, F3, F4, F5, F6 all the way to F14, and in this numbering you will notice that I have pushed the reactions towards the end of that numbering system. If you treat this as a simply supported system, at the extreme left support you have a vertical reaction and a horizontal reaction. Those are labeled F12 and F13, and at the right side you have F14 acting upward or downward. Is it clear? So these arrows show joint forces. Some of those joint forces are support reactions and some of those joint forces are potential loads, and with this kind of description you have a complete description of the external forces on a structure, some of which could be unknown reactions. Is it clear? So here I have shown a free body of that structure, but the force field in a structure also includes internal forces, and there are 11 bars in that structure. Each one has an unknown axial force which could be tension or compression. So if we take out, for example, the bar number 11, if you take a free body of that bar, I have shown an axial tension in that bar. The internal force is marked as N11. N stands for normal force, and here is another picture which shows the possible displacements in the structure, and we will use the same numbering system. If you have F1 and F2 at that top corner joint towards the left and right, we have the same labeling system for displacements D1 and D2. So 1 and 2 are sometimes referred to as coordinates. They are kind of unit vectors because they identify both the location and the direction of either a force or a displacement, but they are all external. Okay, the forces are external to the structure, so are the displacements, they act at the joints. So you can have, if you have, you can have 14 values of displacements. Now let us look at that same bar and see it has displaced in a certain manner. You will find that the movements at the two extreme joints, which we have labeled here D9, D10, D5 and D6, will decide, will dictate how much that bar has deformed, because this is simple geometry. This is called compatibility. So the bar, let us say it has elongated, and we label the elongation E11, E standing for 11. Clearly E11 must be a function of the joint displacements, vertical and horizontal. So if you look at the displacement field is made up of joint displacements, which I have labeled dj, and member elongations, which I have labeled ei. J can vary from 1 to 14 in this case, and I can vary from 1 to 11. And conjugate with this definition, you have Fj, the joint forces, which J can vary from 1 to 14, and Ni, the internal axial forces, I can vary from 1 to 11. Is this clear? So this is a kind of simple framework which is useful for us. The important thing to note is all the forces must satisfy equilibrium, and all the displacements must satisfy compatibility. Now you are familiar with static indeterminacy. It is important to know this new term called kinematic indeterminacy. It is very simple. Our real task in structural analysis is to know everything about the force field and the displacement field, right. In the force field, you saw earlier there were some knowns and some unknowns. The knowns are the loads that are applied, the unknowns are the reactions and the internal forces. That is a force field. As far as the displacement field is concerned, usually everything is unknown. Okay, the displacements are not known and the bar elongations are not known. If we wish to, we should be able to calculate everything, and that is the whole idea of doing structural analysis. Now kinematics is concerned with movements, statics is concerned with forces. So in a truss the movements are joint movements, which are translations in the x and y directions in this example, and the elongations in the different members. Is it clear? So we also found that it is enough to talk about joint displacement, because once you know the joint displacements, you also know the bar elongation, because there is a compatibility which ties the bar elongations to the joint displacement. So indeterminacy in a kinematic sense in a truss is related to only joint displacements. Now in this problem you have 7 joints, and in each joint you can have 2 independent degrees of freedom, that is in this case a horizontal and a vertical translation, and so the degree of kinematic indeterminacy you say here is 14, except at those locations where you have provided supports, because the support ensures that there is no translation. So in this example, if it is simply supported, one would say that D12, D13 and D14 are known to be 0. So your indeterminacy now, the kinematic indeterminacy reduces from 14 to 11, 14 minus 3, because you know the displacements there are 0, is 11. So a truss is a nice example of a structure, this particular truss, which is statically determinate. Ns is equal to 0. The degree of static indeterminacy, if you make it simply supported, is 0. You could also make it into a cantilever, it does not matter. But the degree of kinematic indeterminacy is huge. That is why if you were to solve this problem manually, you would not try the displacement method, you will try the force method of analysis. Okay, so this is kinematic indeterminacy, and you could define it as the total number of degrees of freedom which are independent displacement coordinates at the various joints in a skeletal structure. Let us shift from the truss to a beam element. So I am isolating a beam element AB, and you can see clearly that at the joints there are 4 movements possible, and they are independent. D1 refers to a vertical translation at A, D2 refers to a slope, a rotation at the same location A, D3 refers to a vertical translation at B, and D4 refers to a rotation at B. And I have chosen some directions, you can change those directions. I have shown upward is positive and anti-clockwise is positive. Okay, so here you would say a beam, this particular beam element has 4 degrees of freedom. You can arrest all the 4 degrees of freedom as you would in a fixed beam, fixed beam, and that is interesting. The fixed beam is kinematically determinate. It is strange. That which is kinematically determinate is statically indeterminate. Okay. The fixed beam is kinematically determinate. The cantilever has a degree of kinematic indeterminacy of 2, because on one end you do not allow movements, on the other end you can have a translation and a rotation. Does it make sense? If you have a continuous beam, then you can see that there are 4 movements possible, 3 rotations and 1 translation. If you have a plane frame element, you have 2 additional degrees of freedom compared to a beam element, because the 2 ends can move, 3 and 4 can move, and it is possible for that member to elongate. One assumption we often make is that axial deformations are negligible. If you make that assumption, then 1 and 4 are not independent, D4 and D1 may be interrelated, but otherwise you can have 6 degrees of freedom. So if you take a portal frame with the bottom of the columns as fully fixed, you have 6 degrees of freedom. The kinematic indeterminacy is 6, I have labeled them as 1, 2, 3, 4, 5, 6. But if you ignore the axial deformation, that 6 reduces to 3, because the 2 columns will not change their lengths, so there is no vertical movement possible, and the sway is the same for the entire frame. That means if that beam element will move horizontally, the left end and the right end will move identically. Does it make sense? There is another example of a box frame. Let us take a proper multi-bay, multi-storied building. Now what is the degree of static indeterminacy? The answer is given here. Each box will have an indeterminacy of 3, and there are many ways of finding this out. You know the tree example, you cut it into different trees, the tree is just, rigid and statically determinate. So you need to make a cut on every beam, so that, and every location where you make a cut in a plane frame, you expose how many unknowns? 3 unknowns. You will expose a bending moment, a shear force and an axial force. So how many beams are there? There are 4 into 3 beams, 12 beams, and every cut is 3, so 12 into 3 is 36. Okay. Another way to look at it is every closed box has an indeterminacy of 3, and there are 4 into 3, 12 closed boxes there. The bottom also is like a closed box, and that is how you get. So you have 36 redundants in that structure. So the degree of static indeterminacy is 36, but the degree of kinematic indeterminacy is worse, because you see how many joints do you have which can move? You have 4 in each column, 4 into 4 is 16, and each joint can move horizontally, move vertically and rotate. So you have, except the base, so you have 16 to 3, 48. Okay. The only advantage is if you take advantage of the fact that axial deformations are negligible, you can reduce at 48. Can you tell me how much it will reduce to? it reduces to 16 rotations, but there are 4 sways possible, right, because the whole floor as a whole can move to the left or to the right. So you have 16 rotational degrees of freedom and 4 translational degrees of freedom. So if you make this assumption, then the degree of kinematic indeterminacy is much less than that of the static indeterminacy, and so you will find that the displacement method is a good option. So now let us look at the loads. There are 2 types of loads. You can have direct actions and you can have indirect loading. I hope you remember this, and the response is made up of the internal forces, the support reactions and the displacements. Generally we wish to know everything about the force field, but we may not be interested in knowing all the displacement, just a few critical maximum deflections here and there. So that is the difference between the force response and displacement response. And the direct actions and the internal forces and support reactions put together make up the force field. The internal forces in a skeletal structure are made up of axial forces, bending moments, shear forces, and they could vary from point to point along the length of every element. Whereas the indirect loading is usually a disturbance in the displacement field. What are the types of indirect loading that you expect in a structure? Support settlements, temperature, shrinkage, environmental related loads, which are not very obvious, and no, those are all direct actions. There is a third type of loading, indirect loading. Constructional errors, for example lack of fit in trusses. Well, how do you know that your solution in structural analysis is correct? You need to have some checks. So if you have an indeterminate structure, you can have multiple solutions. How do you know which solution is correct? So the laws of mechanics suggest that you have to ensure that these 3 requirements are satisfied. First, all the forces should satisfy equilibrium. Your force field should be statically admissible. Number 2, your displacement field should be compatible. So these are important words to remember. Equilibrium has to be satisfied, compatibility also has to be satisfied, and finally the relationship between forces and displacements, the force displacement relationships should also be satisfied. Now the force displacement relationships have 2 aspects to it. One is the stiffness flexibility aspect that comes from the stress strain relationship of the material, and we deal with linear behavior, so you need to have a modulus of elasticity well defined for the material. But there is another aspect which is related to the geometry of the structure. So stiffness has both the elastic property of the material as well as the cross sectional, second moment of area, cross sectional area and so on. Indirect loading, as we mentioned, are these 3 types, and it is important to note that this can induce a force response if the structure is over rigid or statically indeterminate, otherwise you will get only a displacement response. So if you have a simple plain truss and all the bars, let us say, had a lack of fit or they had different temperature exposures, that would cause all the joints to move and the truss will adjust itself, but there would be no internal forces or reactions. This is an example of a cantilever beam where the support has rotated. There are no forces, there is a displacement response, but there is no force response. Similarly, you have a simply supported beam where you have a differential settlement, the straight line remains straight, so there is no change in curvature, no bending moment. These are examples of just rigid structures where you have rigid body movements and no force response. But now you take the same cantilever beam with a prop, it is called a propped cantilever beam, and you do the same rotational slip, you will find that kinematically for the beam to return to position B, you have to have a change in curvature. The moment an initially straight beam undergoes a change in curvature, you know for sure there are bending moments that come into play, and the same is true of a fixed beam. So here are examples of internal forces and support reactions being generated by differential settlement. You do not have a problem of internal forces and reactions if the structure is statically determinate, just rigid, but you do if it is not. Constructional errors, lack of fit in trusses. You have an internally just rigid plain truss on the left side, and you have an extra member, a redundant member, which makes it over rigid. Let us say the bar AC is too long. In the first case, all the bars will just adjust themselves. There's, every bar gets the length that it is given, and the joints will move a little bit. How to find these movements is something that you can do by principle of virtual work. You would have studied that. But if you try to do the same thing in an over rigid structure, you will have problems because some bars will have to be necessarily stretched and some will have to be contracted. So you have an internal force field created which is self equilibrating. So that is an important point to note. Okay. Environmental changes, let us take a rod like this which is free to elongate, so there is no force, but let us restrain the other end. Either we prevent the movement fully or we put a spring there, and then you have an over rigid structure, you have an actual force, and you can, and how much it moves depends on the stiffness of that spring. So in summary, the structure must satisfy equilibrium, the analysis must satisfy equilibrium, so that you get static admissibility, compatibility must be satisfied, you get kinematic admissibility, and force displacement relations involving material stress strain laws should also be satisfied. Very quickly, this is very elementary. What do we mean by force response? Well, in a truss, it means you need to know all the support reaction and all the internal forces. So if you take the overall free body of that truss subject to the load P, it is easy to calculate the support reactions. You can use a triangle of forces if you wish, or you can use direct equilibrium. But if you examine very closely that support, if you separate out, you have an action and reaction coming into play. That is Newton's third law. So you must realize that there are many forces coming into play, but they are really related to one another, and you must know how to appreciate the different forces. Okay, this is elementary. Linear elastic behavior, and I have asked this question earlier. Let us say you do a tension test on a material. You can do this in the laboratory. You apply a tension P and the bar elongates by E. You plot P versus E, you get a straight line if you have linear elastic behavior. When you unload, it will retrace that path and go back to the origin, but you will find that this line will depend on the type of specimen that you test. So you could play with different diameters of that specimen. You have big areas of cross section which are larger and which are smaller, and you can also change the length of the specimen, right. How will this line change? Let us say you get so many lines, okay. When will the line be steeper and when will it be flatter? Intuitively. When the area of cross section is larger, the line will be steeper, which means the member is stiffer, the axial stiffness is larger, and if the length of the member is more, what will happen? It will become flatter, it is more flexible, it is easier to pull it. Okay, that is true. So science is all about trying to reduce all these different lines into a single line, and how will you do that?
Multiply.
Stress by strain. E by L.
Right, you redraw these graphs dividing the ordinate P by the cross sectional area A, you get stress, normal stress, and E by L you get axial strain, and you will find that you get a single line which brings out the common material property in the member. So this is a simple understanding of elastic behavior. And if you look carefully, force displacement relationships, P by delta is, if you reduce the element to a spring, to an elastic spring, you use the word spring stiffness, right? That's called axial stiffness in this case, and you will find that P by delta is the same as N by E, for the simple reason that N is equal to P and E is equal to delta for a single element. So if you have different bars, you can define axial stiffness Ki for the ith bar as, you can prove it to be Ea by L, okay, from the definition. So we will conclude with this last slide on displacement response. Force response was finding internal forces and support reactions. Displacement response all about finding essentially deflections and rotation. So if you take that same example, once you know the internal forces, you know the bar elongations by dividing the actual force in each bar by its axial stiffness. Axial stiffness is Ea by L, and if you try to plot this, you will find that the bar 1 wants to elongate and the bar 2 wants to reduce in length. So with center at A and radius AB plus E1, you try to draw an arc, it will come vertically, and so this way of construction is possible geometrically. This is called the classic Williott-Moore diagram. So it is possible to locate the fresh location of the joint B, and that is how you get the vertical and horizontal displacement. So the idea of showing you this slide is to convey to you that there is a strong relationship. We will see in matrices there is a matrix relationship which relate E1 and E2 to D1 and D2, D1 being the horizontal deflection and D2 being the vertical deflection. So this is a kinematically admissible response. We will stop here, we are just doing a review, we will continue in the next class. Thank you.